Hello everyone, welcome to MEC 3323 Solid Mechanics Laboratory. This is your instructor Noshad Arslan Islam. On this video, we're going to be covering tensile test of materials. The main aspects are going to be stress and strain curve, the experiment, the experimental procedure, and the report. The main objective of this experiment would be producing a stress and strain curve for different materials or different objects. So before we talk about a stress and a strain curve, we need to know a little bit about what is stress and what is strain. So stress is the measure of an external force acting over the cross-sectional area of an object. You can define stress as the internal forces acting in between the molecules of the object under this external force. Stress can be defined as by sigma, and it is basically the ratio of force over the cross-sectional area. You can see from the picture that the cross-section, the force and the cross-sectional area direction. There are usually two types of stresses. One is a normal stress and the other is a shear stress. The normal stress usually works perpendicular to the cross-sectional area, while shear stress works when the force is actually applied parallel to the cross-sectional area. The strain. Well, strain is basically the deflection a material undergoes when you apply an external force onto it. To define a strain, it is basically the ratio of deflection normalized by its original length. So it is the deflection delta L and divided by its original length L naught. The strain is basically defined by epsilon. Now, when the external force is applied on a material and you are pulling, so basically when you're in tension, you see the material elongating on the force direction. However, while it elongates on the force direction, there is also another elongation occurring on the perpendicular to the force direction, where the material starts to shrink. So you can see on the diagram that on the x direction the material is elongating, but in the y direction the material is decreasing in length. So it's having a decrease in cross section as well. So to actually define this, we use a term called Poisson's ratio. The Poisson's ratio is basically the strain between the strain in axial direction and the strain in lateral direction. And since you'd always have elongation in one side and reduction in other side, so there's always going to be a negative. Outcome. So to actually make Poisson's ratio a positive term, you use a negative sign in front of it to make it positive from taking into account the negative sign of the ratio. So Poisson's ratio is usually given by nu, and it is defined as minus epsilon x, that is strain in the axial direction, divided by strain in the lateral direction. Now let's talk about the stress and strain curve. Here you can see that stress is plotted along the y-axis and the strain will be plotted along the x-axis. So this is a general typical stress and strain curve for ductile material. So the things that you'd see: a proportional limit or elastic limit, a yield point, an ultimate strength point, a fracture point, and plastic regions and elastic regions. Now, what are the main things of interest are modulus of elasticity, yield point or yield strength, and ultimate strength of a material from a stress and strain curve. So what is the modulus of elasticity? This is basically the measure of an object for or substance's resistance of being deformed elastically under external force. So this region of the stress, this region is basically the elastic region of the stress and strain curve. You can see from O to A on the stress and strain curve, the stress and strain changes linearly. So um, the slope of this linear portion is called the modulus of elasticity. On this region of the stress and strain curve, Hooke's law can be applied, and basically sigma stress is equal to E epsilon, where E is our modulus of elasticity and is the slope of our linear portion of the stress and strain curve. Now yield strength. Yield strength is the point or on the stress and strain curve where you'd have permanent deformation or plastic deformation. So if you go beyond the yield point on a stress and strain curve, you'll start seeing plastic deformation on your material. The yield strength or the stress is the stress at which the material will retain at least 0.2% of permanent elongation after the force or the stress is removed. For some ductile materials, it's 0.2% elongation because the plastic deformation and the elastic deformation is very hard to differentiate. However, there are materials where you can actually locate the yield strength more easily, and on those cases, it's just the point after which you see plastic deformation. So, ultimate tensile strength. Well, this is the strength that this is the maximum strength that a material can withstand. After this, usually the material starts to fracture. So it is that actually the maximum stress you see on a stress and strain curve for for a certain material. Now elastic region, this is the region that's up to yield strength. So this is the region where you see the material deforms elastically. So once the force is removed, you see that the material will go back to its original length. Now, the plastic region is the point beyond the yield strength. So on plastic region, even if you take off the force, once a material goes into the plastic region, it won't come back to its original length or its original state. Now, strain hardening. Strain hardening is basically the region from yield point to the ultimate stress or ultimate tensile strength. So in this region, the material starts to deform plastically, so it removes the yield point to the right and increases your yield stress or hardens the material, so you are going more closer to fracture. Now another interesting thing for ductile material on the on the stress strain curve is necking. So necking is basically reduction in cross-sectional area. So it occurs after you cross the ultimate tensile strength on the stress strain curve. So once you cross that point, you start seeing your cross-section of the material start shrinking drastically, and uh, and at some point it would fail. Um, so in case of engineering stress and engineering strain, necking is usually neglected because on that part of the curve you see a reduction in stress with increasing of strain. That is because on engineering stress and engineering strain, you assume the initial um, cross-section of the material instead of taking into account the reduction in the cross-sectional area of the material. So the stress starts going down. However, in case of true stress and strain curve, where stress is basically measured as a function of actual area instead of the original area. So as you or cross-sectional area reduces due to necking, your stress would also increase. So on that note, on a true stress and strain diagram, you see increasing stress with strain on a stress strain curve. Now, what are the key points on a stress and strain curve that you should be looking into? Why is it required? So you can see different materials have different stress and strain curve pattern. So if you see the metals, they use or a ductile material would first deform elastically until it goes to the yield strength, then it would deform plastically until it reaches the ultimate tensile strength and then fracture. In case of brittle materials or ceramics, you see they deform elastically, and after some point they cannot take a lot of plastic deformation. Once they reach the yield point, they fracture. In case of plastics or polymers, you see they are very good at deforming plastically for a long period of time, but after they go over the elastic deformation period and the yield strength, there's a drastic increase in the stress and they would fracture. So this gives you actually an idea how to decide upon which material you should choose for your application. And remember, you do not want your material to fail or your object to fail when it's in operation. So you always design for the yield strength of a material. So if you know the yield strength of a material, you know that okay, you can use that material up to in your operation for a certain period of time or in certain operations um, under certain loads. You cannot exceed that loads or you deform plastically and go to fractures. So this is very much required for you to understand what material you need to use for building a plane, a car, or whatever you want to do. So you need to know the property of the material. Now, on this experiment, we're going to be doing tensile testing of 3 different specimens made with PLA. So we're going to use an Admet M-Test Quattro tensile testing machine to pull the specimen in with tensile force and see the fracture and get the stress and strain curve. Now, the 3 specimens, they're going to be 3D printed using PLA. Now, the print orientation is going to be 0 degree, 45 degree, and 90 degree. So, according to the print orientation, the specimens are going to show different amount of strength and different type of tensile stress and strain curve. We're going to try and see how much it differs, and we're also going to try and see all the points and we saw on the stress and strain curve, and we will try to identify those points on our stress and strain curve for PLA. The next part of this lecture would be the experimental procedure and the reporting procedure, which would be covered during the class period. Thank you for listening.